Welcome to iTTV for Form 5 Physics. The title of this lesson, Refraction of Waves. In this lesson, we want to have a look at refraction. We've already studied refraction when we did light. What we understand in refraction is if a light ray strikes a boundary between two medium, one less optically dense and one more optically dense, what will happen is as the light ray travels from less optically dense into the more optically dense medium, it will change direction. It will bend. And why does it bend? It bends because there is a change in velocity. If you go from one medium to another medium, but your angle of incidence is 90 degrees, same with the normal, then there is no apparent change in direction. You keep going in the same direction, but there is still a change in velocity, although we cannot really detect it. In this lesson, we want to have a look at refraction of water waves as they travel through a ripple tank, and look at the keys and the factors that are going to affect our water waves and how they bend, and what are the factors that are changing. Is the velocity changing? Is the wavelength changing? Is the frequency changing? Refraction of waves involves a change in the direction of waves as the waves pass from one medium to another medium of different optical density. Bending of the path of the waves accompanied by a change in speed and wavelength of the waves. The speed of a wave is dependent upon the properties of the medium through which the wave passes. So, if the medium and its properties are changed, the speed of the waves are changed. The most significant property of water which affects the speed of waves traveling through it is the depth of the water. So this is the most important thing, the depth of water. What we need to understand is that in deep water, a water wave travels faster. In shallow water, the water wave is going to slow down. Let's put this up on the board because this is really the key factor that we need to remember for refraction in water. So let's draw just a simple ripple tank. Let's draw it from the side. Okay, let's draw in our water up here, like so. Now inside the ripple tank, let's place a glass block. I'm going to place a glass block over here. Now what we have is deep water over here and shallow water over here. So let's label these deep, and over here shallow. Where your water is deep, you have a high velocity. So here your velocity is higher. As the water travels from deep water to shallow water, in the shallow water the velocity decreases. So here our velocity is decreasing. And this is key. So the big change that we get is when we go from deep water to shallow water. The velocity decreases as we enter shallow water. So in terms of density, shallow water behaves very similarly to more optically dense medium. The deep water behaves like less optically dense. Water waves travel fastest when the depth is the deepest. Water waves that are passing from deep water into shallow water will slow down. In the diagram, you can see as the water is traveling in the ripple tank and the waves pass over the glass block, they are slowing down. Oh no, you can't see that, can you? The problem is you can't really see a water wave slowing down very clearly. What you do notice is the wavelength of the water is decreasing as it enters into the shallow region. This decrease in wavelength is the indicator that the velocity is decreasing. So, in the deep water, you have a longer wavelength, but in shallow water, you have a shorter wavelength. So here what is key is the relationship between velocity and wavelength. Now, velocity and wavelength are directly proportional to each other. If the velocity increases, the wavelength becomes longer. If your velocity decreases, your wavelength becomes shorter. Now let's apply this idea to the diagram up here. Over here we have a high velocity, which means the wavelength is going to be long. Lambda is also great. In the shallow region, our velocity is decreasing. And as we saw, the wavelength in the shallow region is a shorter wavelength, which means that lambda here is also decreasing. Now, if we were to draw this up here, what we would get are wavelengths that were long in the deep region, and as the wave moved into the shallow region, our wavelength becomes shorter. So we have long wavelengths over here and short wavelengths over here. Because the wavelength is becoming shorter, we can basically then say that the velocity is also decreasing. Like I said, it's very hard to see the velocity change in the ripple tank, but what is easy to see is the change in wavelength. So the key, the thing that you really need to realize is that your eyes must be looking for this wavelength change. If you see the wavelength change, then you know refraction is occurring and the velocity is also changed. Here in the deeper water, the wavelength is wider. Here in the shallow region, the wavelength is narrower. Water waves travel fastest when the medium is the deepest. Thus, if water waves are passing from deep water into shallow water, they will slow down. This decrease in speed will also be accompanied by a decrease in wavelength. So, as water waves are transmitted from deep water into shallow water, the speed decreases, the wavelength decreases. So remember, deep water, fast, shallow water, slow. Wavelength, deep water, long, shallow water, shorter. Good. And if we take both of these together, we can get a formula from these two that will allow us to calculate the change in either velocity or wavelength. We get this formula, which says V1 over lambda 1, which is in the deep water, is equal to V2 over lambda 2, which is in the shallow water. Meaning the ratio of velocity to wavelength in deep water will be equal to the ratio of velocity and wavelength in the shallow water. Frequency is unchanged. The frequency is unchanged because we're using the same vibrator. Nothing is changing in that circumstance, so the frequency in both the deep water and shallow water are the same. Let's make a note of this. Frequency is unchanged. Why? Same vibrator is used. So you're using the same vibrator, so your frequency is unchanged. Okay? But V and lambda are going to change. Now, a typical type of question you might get in the examination is one that's showing you these wavelengths and is asking you where is the deep water and where is the shallow water. Let me draw a diagram for you and let's go through this question. Let's say that they give you a diagram like this, similar to the one that we have over here. And let's say that inside here we have a surface that is becoming like this. On top here is our water, and here I drop a stone. Now notice that over here we have shallow, over here we have deep. What is the wave going to look like that you produce? Well, if you drop a stone into the water, you're going to get pretty much a circular wave being produced. Now over on this side, it's going from deep to shallow, like so, which means that your wavelength must be decreasing or increasing. Good, decreasing. So what we should be getting on this side are wave front that are becoming closer to each other on this side. Over here, we're going into deeper water, which means that the wavelengths should be becoming longer. So on this side, we should get wave front that are going further and further and further away from each other. So what you're going to see is on this side, the wavelength is becoming shorter. Over here, the wavelength is becoming longer. So these are typical types of questions where they're asking you to visualize what is happening when you drop or create a vibration or a wave, and you have the wave traveling into two different types of media, meaning they're going into a shallow area and they're going into a deeper area. So what are you going to see? Once again, remember, we cannot see the velocity change. What we can see clearly is this change in the wavelength. Experiment lab, refraction of water waves. Aim: to observe what happens to water waves as the wave passes from deep to shallow water. Apparatus: 1 ripple tank and accessories. Procedure: set up a ripple tank. Put a glass plate in the ripple tank. Pour water into the tank until the plate is covered by half a centimeter of water. Send straight waves to hit the edge of the plate head on. Draw your water wave front in the diagram. So, if you've got a situation like this where you have plane waves approaching a glass plate, what are you going to see as the plane waves go over the glass plate? Now the glass plate represents a shallow area. Are your waves going to become longer, or are your wavelengths going to become longer, or are your wavelengths going to become shorter? Which one are you going to see? Draw it out. Good. Well, let's see if what you've got is going to be similar to what I sketch up here on the board. So if I have plane waves and they're approaching a glass block like so over here, which is the shallow area, as my plane waves strike the shallow area, the waves on the outside should be unchanged, but the waves inside should become narrower, like so, because here my wavelength diminishes. So we should get a change that looks something like that, where over the shallow area the wavelength is shorter. There's no change in direction here because your angle of incidence is 90 degrees to the surface. Now let's have a look at the ripple tank again, but this time we've turned the glass block. So here we are definitely going to get a change in direction because the angle of incidence is not 90 degrees. Notice the waves that are being produced. Now let's try and sketch what we've seen on a diagram. So in this case, we're getting an angle coming in. How do we do this? How do we draw the change in direction? Well, the idea is very similar to when we do light. Draw a line of propagation, draw a normal, work out which way your wave is going to move, and then put in your wavefronts. Let's work together and do one. So what we have is a wavefront, like so, that is approaching our glass block, and our glass block has been placed at an angle like this. Now, as this wave is about to approach here, let's draw in our line of propagation. Our line of propagation, let's work at the top here, or work at the bottom here actually. So our line of propagation is like so. So we strike here. Remember, draw in your normal. Once you've drawn in your normal, remember we're going from deep to shallow. Shallow behaves as the more optically dense, which means that the water wave propagation should go this way, like so. So, now that you've worked out your new direction, on this line, draw in your water wave front, and remember, they must be closer to each other. Outside, there should be no change in wavelength. It's only inside, on top of the glass block, where they're changing. So once again, complete your line of propagation, draw in your normal, work out the change, whether you're moving towards the normal or away from the normal, and then draw in your wave fronts, remembering that in the shallow area, your wave fronts have to be shorter. Oh, sorry, not your wave fronts, your wavelengths have to be shorter. Everyone understand? So, complete the line, draw the normal, draw the new direction, and then fill in the wave fronts, clearly showing that the wavelength is shorter. Good. So you should get a diagram that looks something like this. Discussion. When water waves pass from deep water to shallow water, refraction takes place. Remember, the frequency is unchanged. The wavelength decreases and the wave speed decreases. If the water waves hit the shallow deep water boundary at an angle, there is also a change in direction. Let's try an exercise. The diagram shows the wave fronts of a plane wave in a ripple tank. The wave incident from deep region to shallow region in a ripple tank. Which statement is correct about the refracted and incident waves? A. The speed of the refracted wave is the same as the speed of the incident wave. B. The wavelength of the refracted wave is shorter than that of the incident waves. C. The frequency of the refracted waves is lower than that of the incident waves. D. The direction of the refracted waves are always at right angles to the incident waves. So remember, when we do this, think about what changes. We've got the list here, so remember your frequency is unchanged, which means that really the answer for C is incorrect. When we go into a shallow area, the velocity decreases. So answer A, where the velocity is the same, must be incorrect. Remember, your wavelength in shallow is less or has decreased compared to that in the deep. Now this is pretty much what answer B is saying to us. So the correct answer is B. The wavelength of the refracted waves is shorter than that of the incident waves. Why a wavefront changes direction? Waves are traveling from a less dense medium to a denser medium, from deep to shallow. Wave traveling with a velocity v1 in medium 1 and wavefront shown enters medium 2. It will travel more slowly than the right-hand side of the wavefront. The wavefront on the left-hand side moves slower as compared to the wave on the right-hand side of the wavefront. The change in velocity of the wave causes the change of direction of the wave. The change of direction of light as it passes from one medium to another is associated with a change in velocity and wavelength as well. So this is very similar. Light does the same thing as a water wave. It also changes direction because of a change in velocity. And the reason for the change in velocity is identical. The left-hand side will be traveling slower than the right-hand side, which causes it to bend. Draw the refracted water wave. So in the diagram that you have here, we want you to draw this water wave. Now, remember about the key things as you draw them. Continue with the line. Make sure that after you've drawn the complete line, knowing what the direction of the wave is, then draw in the wave fronts. Remembering clearly that the wavelength in shallow water must be shorter, and in deeper water it needs to be longer. So let's go through this slowly, step by step. So what we have is a shape that is something like this. We've got water waves coming in over here. Now let's draw our line of propagation. Our line of propagation is like this. Now at this area here, your angle of incidence is 90. There should be no change in direction. So the wave should travel straight on. Now as your wave hits this boundary where there is an angle, draw in your normal. You're going from shallow to deep, which means you're going from more dense to less optically dense, which means you should be moving away from the normal. So complete your diagram like so. Now that you've done that, put in your waves. Here you are in a shallow region, so your waves should be closer to each other. Once your wave travels out into the deeper area, once again, your waves should become longer, like so. So you can easily work out what is happening. Just remember and follow the rules. Use the line of propagation, complete it, knowing exactly what is happening to the wave in terms of direction. When you've completed that, then fill in the wave fronts. I'm sorry to keep repeating this, but it's very important that you understand that it's easy to do if you follow simple rules. Finish the line and then put in the wave fronts. Remember, in the shallow area, you must be short wavelength, and in the deeper area, you must have a longer wavelength. Now, draw this one. Here we've got a surface that is circular, so our shallow region is a bit more tricky. Now, here as a rule of thumb, the wave fronts will follow the shape that they first encounter. So in this case, we've got a perspex piece that is circular in shape like this. As the wave fronts approach, just try to remember, like I said, as a rule of thumb, the waves will follow the surface that they first encounter. So the waves here should bend like this, which means they're going to bend to a point and then from a point come back out like so. So try to remember that as a rule of thumb. Once again, remember, in the shallow area, your waves should have a shorter wavelength. Now try and draw it for this. So in this one, you've got a similar type of surface, but it's curved in the opposite way. So remember what I said, you always follow the surface that you first encounter. Try and draw this one. Have you done it? Good. Refraction of sound waves. Sound waves travel faster in warm air than in cold air. So the key here is sound waves will always bend towards where the cold air is. If the cold air is higher up and the warm air is lower down, your sound wave will bend upwards, away from the earth. If your cold air is down and the warm air is higher up, your sound wave will bend back towards the earth. Now, if your sound wave bends back towards the earth, it tends to travel a longer distance. It's also seemingly louder, which is why at night it seems that every sound you hear is a slightly louder sound, because it is traveling through and refracting towards the cold air. On a hot day, the hot surface of the earth causes the layer of air near the surface to be warmer. This causes sound waves to be refracted away from the earth. On a cool night, the sound waves travel slower in the cooler layer of air near the surface of the earth than in the upper warmer air. The waves are refracted towards the earth. Hence, sound can be heard over a longer distance on a cold night compared with a hot day. Summary: refraction is the change in direction of the path of propagation when passing between two media. Waves propagate faster in less dense medium. Waves pass from one medium to another medium of different optical density. Bending of the path of the waves accompanied by a change in speed and wavelength of the waves. Remember the key that we did up here. In the deep water, the velocity is higher, so the wavelength is longer. When you enter into the shallow region, the velocity decreases and the wavelength also decreases. As you pass from the deep to the shallow at an angle, there will be a refraction phenomenon, which means you're going to bend towards the normal. When you go from shallow to deep, you will bend away from the normal. The frequency is unchanged. Remember, with sound waves, you bend away from the earth if the cool air is above, or you bend towards the earth if the cool air is lower down. So during the day, sound refracts away from the earth, and at night, sound refracts towards the earth. That's all the time we have on this lesson. Thank you for watching ITTV.